your introduction.
Okay. Okay, hello everyone. So I'm Christophe Breuil from Orsay, and I am kind of a moderator for this session of number theory. So it is a talk, but it is a pre-recorded talk. So unfortunately, it is impossible, therefore, to ask questions using the tab. But you are welcome to discuss using the Discord channel after the talk. So the talk is by Raphaël Beuzart-Plessis. So Raphaël is a chercheur at CNRS, at the Institut Mathématique de Luminy in Marseille, in the southeast of France, and he's a specialist on the Langlands program, more precisely on the relative Langlands program. And his talk is relative trace formula and the Gan-Gross-Prasad conjectures.
Today, our first speaker is Raphaël Beuzart-Plessis from University of Aix-Marseille and also CNRS. Yeah, so Raphaël was a student of Jean-Luc Waldspurger, graduating in 2013. And after spending a couple of years at IAS, he actually spent the academic year of 2015 and 2016 in Singapore. So we're very fortunate, very happy to have him here for a year, and after which he returned to France. Okay. So without further ado, again, okay, so the first talk this afternoon by Raphaël Beuzart-Plessis from University of Aix-Marseille and CNRS, and he will talk about the Gan-Gross-Prasad conjectures and relative trace formula.
Okay, so thanks a lot for the introduction. And in this talk, I'm going to report on some recent progress on the so-called Gan-Gross-Prasad conjectures with a special emphasis on techniques originating from relative trace formulae. But before entering into the art of the matter, let me describe briefly the subjects of this talk and of the Gan-Gross-Prasad conjectures, which are actually twofold. So as you will see, first, this concern certain relations between automorphic periods and L functions, which is a very old subject, going back in some sense, at least to Riemann. And then there is another aspect to it, which has to do with representation theory. This is the question of bunching laws. So namely, given a group G and a subgroup H, as well as an irreducible representation pi of G, the question you ask is, what are the irreducible representations occurring in the restriction of pi to H? And now I would like to mention that these two themes, and in particular their interrelations, are actually part of a broader picture, now known as the relative Langlands program. And that in this talk, I will really focus on some particular examples that are very important and seminal in some sense, provided by these conjectures of Gan-Gross and Prasad. So I will start by recalling two well-known examples of such relations between automorphic periods and L functions. First is Ecke's theory for modular forms. So let F be a modular form, cuspidal, of weight K and full level N. So here I have recalled the definition, but very quickly, these are holomorphic functions on the upper plane, satisfying a bunch of functional equations with respect to a certain congruent subgroup of SL2Z with a condition at infinity. And these modular forms have Fourier expansions of the form sum of the n q to the n, where q stands for exponential of 2i pi z. And what Ecke noticed is that if you take the L series of that modular form, that is the Dirichlet series formed out of the Fourier coefficients, and multiply it by a certain gamma function, then this is nothing but the Mellin transform of the restriction of F to the imaginary axis. And this simple formula already has interesting consequences, such as the analytic continuation and functional equation for this L function. And there is also another aspect to this theory of Ecke, which comes from the so-called Ecke operators. So namely, Ecke has attached to any prime number P not dividing the level a certain endomorphism of the space of modular forms, Tp. And he has also observed that if you take a modular form which is eigen for all these operators and primitive in the sense that it's roughly not coming from a modular form of smaller level, and as well as normalized by taking its first Fourier coefficient to be 1, then its L series admits also an Euler product of this form. And moreover, in this case, the functional equation takes a particularly simple form because it's relating the value of the completed L function at S and K minus S up to some factor involving a very subtle invariant, which is just a sign here, epsilon f, and which is called the global root number. and which will show up again later. So in order to put these things into a different perspective and generalize it in another context, I will now just reformulate very quickly these results of Ecke in the adelic and automorphic language. So let A be the ring of adels of Q. Then it's very well known and very classical that to any eigenform, as on the previous slide, you can associate a so-called cos form on PGL2. That is a function on PGL2 of the adels, which is left invariant by PGL2 of Q and satisfying a certain number of conditions, the most important being that it's a generalized eigenfunction, meaning that it generates, under right translation, an irreducible representation of PGL2 of the adels, and that we call a cuspidal automorphic representation. So using that language, I can now reformulate and slightly generalize Ecke previous formula. Namely, now we can work over any number field, F, as well as take any cuspidal automorphic representation of PGL2 over that field. And then the analog of the formula of Ecke on the previous slide is that if you take any cusp from phi in the space of pi and integrate it over the subtorus of diagonal matrices, where here I use a notation, so group into brackets, which always means it's adelic points mod its rational points. And you integrate it over that torus against a character given by the absolute value to some power s, then you get back again an L function. L function, the standard L function of pi shifted by 1/2, where this standard L function is the analog of the completed L function of f from the previous slide, except that, so it's defined directly using another product, and it's always normalized so that its central point is at 1/2. And this is a Worf formula because it's not true exactly. And let me make it more precise in the case when you specialize to the central point, that is s equals 0. So since pi is an irreducible representation of PGL2 of the adels, it will somehow decompose as an infinite tensor product of representations of PGL2 over the completion of f, that I denote here by pi v. And if we take furthermore phi to be a pure tensor in this decomposition, specializing the previous formula to s equals 0, we get that the automorphic period of phi over the diagonal torus, that here I denote just by PGM, so P stands for period, is equal exactly to the central value of the L function times a product of local terms, PGMV here, which are actually functionals on the local components of pi that are invariant by the subgroup of diagonal matrices. And moreover, we can show that they are always non-zero. And this has the following interesting consequence about non-vanishing. Namely, from this, you immediately deduce that the central value of the L function does not vanish if and only if this period of Ecke is not identically 0 on pi. Okay, so now I'm going to describe another very famous formula, which is due to Waldspurger. And we start with the same setting as before, except that now we introduce a quadratic extension E of f. And to such a quadratic extension, we can associate a maximal torus of PGL2. Namely, you embed in a natural way the multiplicative group of E into GL2, and then you take the image in the quotient. And this gives you this elliptic maximal torus T. And then you essentially do the same thing as before. Namely, you take a form, a cusp from phi in some cuspidal automorphic representation pi, and you take its automorphic period, so over T, that is, you integrate the form over the automorphic quotient of T. But this time, for Waldspurger formula, you have to take the square of the norm of that period. And what Waldspurger tells us is that this is essentially equal to the central value of another function, which is actually a standard function of the base change by E of pi to PGL2 over E. And again, we can make this formula a bit more precise by using the factorizable structure on pi. So when you take a pure tensor in the space of pi, then the previous formula becomes the following one, where I'm again ignoring some terms, and I will come up later, but for the question of non-vanishing, they will not matter, actually. So you get essentially that the square of the module of the period is equal to the central L value times the product of local terms, where the local terms this time are Hermitian forms that are invariant under the local points of your torus. But the difference with the previous case is that these local periods might well be 0, and we might even have the case where the local constituent of pi does not support any invariant form at all. So it happens sometimes. And this is problematic because in this case, this formula is not telling you anything about the central L value. But fortunately, Waldspurger actually proved the formula, which is much more general. And for this, we need to pass to other groups, which are called the inner forms of PGL2. So let B be a quaternion algebra of F. And we assume that the quadratic extension that we fixed previously embeds in B. Then this B gives us a so-called inner form of PGL2, that is a group of projective units in B that we look at as an algebraic group over F. And the assumption that E embeds in B gives us an embedding of the previous torus in this group G. And then we can do the same thing as before, but we will take a cuspidal automorphic representation of that group G. And then there is a series of Jacobi-Langlans which relates those with cuspidal automorphic representations of PGL2. And we will assume that the Jacobi-Langlans lift of this pi prime is the pi we started with, meaning that at almost all places, or at all places where the local points of G are isomorphic to PGL2 of FV, this happens at all places except a finite number, the local constituents of pi and pi prime are the same. And so starting with pi prime, we can now do the same thing as before and take its automorphic period over T. And there's a similar formula of Waldspurger in this case. So the square of the module of that automorphic period is equal roughly to the same central L value of the base change times the product of local terms, which are of the same kind as before. So these are invariant emission forms or the local constituents of pi prime. But now we can use we can complement this formula of Waldspurger with another result, which is due to Tunnel and Saito. So telling you exactly when these local periods are non-zero. So namely, first we have an equivalence which is relatively easy to show in this setting, that the local period is non-zero if and only if the local constituent of pi prime does support a TV invariant form. And then the Tunnel-Saito theorem tells you that this is the case if and only if a certain local root number associated to the base change of pi, so this is a certain family of numbers whose product is the global root number of pi e, is +1 when the group is split at V, meaning that the quaternary algebra becomes isomorphic to the algebra of 2x2 matrices, and is -1 otherwise. Okay. And when you combine these two results plus Jacobi-Langland theory, you end up with the following theorem, which is also due to Waldspurger, telling you, so this is again a non-vanishing statement, and it tells you that the central value of the base change L function is non-zero precisely when there exists a pair B pi prime as before, so B is the quaternary algebra over F, satisfying the condition that it contains a copy of E, and pi prime a cuspidal automorphic representation, which is related to pi as above, such that the Waldspurger period, that is the automorphic period over T, is non-zero on pi prime. And moreover, we can also deduce that the pair B pi prime, that if it exists, is unique. Okay, so it ends my discussion of the two examples of relations between central L values and automorphic periods. And now we will try to, we'll discuss the Gan-Gross-Prasad conjectures, which is in some sense a generalization of that result of Waldspurger in higher rank. So in order to motivate a bit what is coming next, let me just summarize what we have seen so far. So EQ periods was related to the embedding of GL1 in PGL2 as the diagonal subgroup. And one natural way to generalize that in higher rank is to consider the natural embedding in of GLN in GLN+1. And this indeed leads to something meaningful, which is called Rankin-Selberg theory, and which was developed by Jacquet, Piasecki-Shapiro, and Shalika. And, but okay, this is another story. What interests us is a generalization of a Waldspurger formula. So take again the group and the subgroup that we have considered on the previous slide. So the group was this inner form PB star of PGL2, and the subgroup was this maximal torus T. And we can look at this pair in at least two different ways. So either we can see it as the embedding of a unitary group in one variable in the projective unitary group in two variables, or we can look at it as embedding of a special orthogonal group in two variables into a special orthogonal group in three variables. And this leads to two natural generalizations of Waldspurger formula, which are corresponds to consider the embeddings of any unitary group in n variable into any unitary group in n+1 variable, or the same thing for special orthogonal groups. And there are actually indeed conjectures in these two cases that are due to Gan-Gross and Prasad. And for simplicity, and also because in some sense the results are more complete globally in this case, I will only focus on the unitary setting in this talk. Okay, so let me now start to introduce the global Gan-Gross-Prasad conjectures. So this setting is as follows. You take E over F, a quadratic extension of number fields, as well as a pair of Hermitian spaces, W0 and V0, of respective dimensions n and n+1, with W0 included in V0. So in other words, W0 is just a non-degenerate hyperplane in V0. And we'll introduce now a pair of groups, which are G and H. So G is just the product of the two unitary groups, and H is the small unitary group that is the unitary group of W0 that we embed diagonally in the product in the natural way. And so we are going to associate to this situation two kind of invariants as before, which are the two main ingredients for the conjecture. So the first main ingredient is the automorphic period. So namely, we take, as before, a Cuspidal automorphic representation of that group G. Since G was a product of two unitary groups, it naturally decomposes as a tensor product of Cuspidal representations of UW0 and UV0. And for any form, cusp form phi in the space of pi, we can form this automorphic period, which is the integral of phi over the subgroup H, or rather over the automorphic quotient of H. So this is the first ingredient as before. And then as for Waldspurger formula, we need the L function. And this L function is again coming from the base change of pi. So namely, we'll have to introduce another automorphic representation, pi e, which is going to be an automorphic representation of GLN times GLN plus 1 over e, which is the base change of pi to e. So it's a particular case of Langlands functoriality, and it will actually be decomposed as a tensor product of the base change of pi w and pi v. And the existence of those base change was obtained rather recently following the work of Arthur for other classical groups, then adapted to quasi-split unitary groups by Mock, and then in general for non-quasi-split unitary groups, this is work of Kaleta, Mingeshi, and White. But once you have this base change, you have two automorphic representations of GLN and GLN plus 1 over E, and you can form the so-called Rankin-Selberger function. And this is the second main ingredient for the conjecture, with the caveat that, as before, we'll actually have to vary the groups, and rather than vary the groups, here we'll be varying the Hermitian spaces. So namely, we will fix the orthogonal complement of W0 in V0, we call it L, and then we will vary W0, and we take for any n-dimensional Hermitian space W, we consider the following pair of groups, where, so this is defined exactly as before, where you replace W0 by W and V0 by V, where V is the orthogonal direct sum of W with L, okay? And so the situation is exactly the same as before, and you can define exactly the same objects for that pair of groups. And we also need a way to compare automorphic representations on different groups, so I introduced the notion of near equivalence here. So if you have also a Cuspidal automorphic representation of one of those groups, GW, we'll say that it's nearly equivalent to pi if, as before, for Jacob-Langlands lift, for almost all place V, the local components of pi and pi prime are isomorphic. And to make sense of this, you have to notice that for almost all places V, the Hermitian spaces are all the same, and therefore the unitary groups are the same, and the groups are isomorphic. So with all this in place, we can now state the two main global results here. So the first one, the two theorems are going to state, followed from a series of works. So I have written the name of all the people that have contributed here, and I will come back to their respective contribution later. But we can now state the following theorem, formerly known as the Gan-Gross-Prasad conjecture. So namely, we have to assume, so there is a small technical condition that pi e is generic. And then, so this is similar to Waldspurger theorem. There's an equivalence between the two following statements. First, the central value of the base change L function is non-zero. And secondly, there exists n-dimensional Hermitian space, W, as well as a Cuspidal automorphic representation pi prime of the associated group GW, which is nearly equivalent to pi, and such that the Gan-Gross-Prasad period is non-zero on pi prime. And as in Waldspurger setting, moreover, the pair we obtain in this way, W pi prime, if it exists, is unique. I should also mention, before passing to the next slide, that actually part of this theorem was known before because the implication 2 implies 1 was actually proved by another technique, by work of first Ginsburg, Jung, Rallis, then Ichino, Yamada, and completed recently by Jiang and Lei Zhang. So the second main global theorem is a direct generalization of Waldspurger formula. So let me show you this formula. So it's similar in spirit. And it says that under a slightly more stringent assumption, which is actually not completely necessary, but let's ignore this one, that for any factorizable factorizable vector in pi, we have the following factorization of the square of the module of the Gan-Gross-Prasad period. So on the right-hand side, let me describe the terms. So we still have this is the main term in some sense, the central value of the base change L function. Then I've added there is also some adjoint L function at 1, which doesn't have any pole at 1 in this setting, so that it's cannot contribute to the vanishing of the right-hand side. Then there's another very subtle global invariant S pi, which is actually a finite abelian two-torsion group, which in some sense is describing the structure of the global automorphic packet of pi. That is a set of automorphic representations that are nearly equivalent to pi. And then we have a product of local terms as before, where I can now give you a formula for these local terms. So these are essentially given by integrating the corresponding matrix coefficients over the subgroup of local points of the group H. And this is normalized by multiplying by the inverse of this ratio of L functions locally. Anyway, so there's a formula like this, and actually I didn't write all of it because, so here there's a isomorphism sign, which means that I've written a formula which is true up to some abelian L factors, which I didn't bother writing because it will overcharge the slides somehow. Okay, so, and this was formerly called the Ichino-Ikeda conjecture, and this is also a consequence of the same set of works that has established the Gan-Gross-Prasad conjecture. So now in the next 2 slides, I will give a quick overview of the proof of these 2 global theorems. So the basic starting point is an approach due to Jacquet and Rallis. They have proposed to attack these conjectures through a comparison of so-called relative trace formulae, which actually are generalizations of the well-known Arthur Selberg trace formula, and which, roughly speaking, relate automorphic periods to more geometric distributions known as relative orbital integrals. So rather than describing the general theory of those trace formulae, let me just give you approximative forms of the 2 relative trace formulae that we'll need. So there's the first one, which is related to the Gan-Gross-Prasad period, and so very roughly speaking, it takes the following form. So this is an equality of distributions on the adelic points of G. So both sides depends on the test function f here. And I put the equality in quotation marks because it's actually not true as written. It's ignoring very serious analytical and convergence issues that I will come to back again afterwards. So on the left-hand side, you essentially have a sum of rational double cosets of H in G, where for any delta in this double coset, you have a sum of distributions O delta, which are essentially given, at least when delta is sufficiently regular, as the adelic integral, the integral over the adelic points of the corresponding coset of the test function. And this is for delta sufficiently regular. So here the part I'm ignoring is the part corresponding to singular orbits where this integral does not converge and there is an issue and it has to be regularized in some way. And on the right-hand side, on the other end, you have a sum of some orthonormal basis of the space of Cus forms of terms which are essentially products of 2 Gan-Gross-Prasad periods, one of them being composed by right convolution by the test function. And this is really the main contribution on the right-hand side, because here I'm ignoring other contributions coming from the non-cuspidal part of the spectrum, which is where the convergence and analytical issues are hidden. But anyway, this is the first approximation of the formula. And Jacquet and Rallis has proposed to compare it to another one, which is similar in nature, but where you have to replace the group G by another group G prime, which is the product GLN and GLN plus 1 over E. So remark that this is exactly the group where the base change is living. And you have to replace H by 2 subgroups. So H1 is GLN over E embedded diagonally in the product, and H2 is just the same group defined over F. And so the formula is very roughly of the same form. So on the left-hand side, you have a sum of over rational double cosets of relative orbital integrals, which are defined in the same way, at least for sufficiently regular double cosets. And on the right-hand side, you have a sum of products of two periods. So one is over this subgroup H1, this is an automorphic period. And the other one is over that subgroup H2. Actually, technically, you have to twist it by some small character, but I will ignore this part during this talk. So one reason why we could expect these two relative trace formulae to have something to do with each other is actually that we know a lot about the two periods appearing on the right-hand side of the second formula. Namely, the first one, the automorphic period of H1, has been studied by Jacquet, Piasecki, Shapiro, and Chalika as part of Rankin-Selberg theory that I mentioned before. And in particular, they have shown that when you restrict it to a certain cuspidal automorphic representation, it essentially gives you the central value of the corresponding Rankin-Selberg L function. And in particular, this is non-zero on that cuspidal automorphic representation if and only if the central value is non-zero. Whereas the second period over H2 has been studied by Flicker and Rallis, and it's actually, it's non-vanishing, it is exactly detecting the image of base change from G. And if you combine these two facts, you, in some very rough sense, you see that the two right-hand sides, which are also called the spectral sides of the two relative trace formulas, are related in some way. So there's some kind of matching. And the idea of Jacquet and Rallis is that we can prove precisely such a matching by comparing directly the left-hand sides, also called geometric sides. And the comparison they have proposed is following the usual paradigm of endoscopy, that is doing equaling the two sides term by terms. And this requires first to get a matching between the indexing sets on both sides. And this is this is something that was defined by Jacquet and Rallis, and there is a correspondence between double cosets on both sides for any field extension of F. So here we'll only take K to be the base field F or one of its completion. And once you have such a matching, you can define a certain notion of matching of test functions actually. So this is now a local notion. So for test functions F, V, and F prime V on the two sides, we'll say that they match if for any sufficiently regular orbits that are matching on both sides, the orbital integrals, the corresponding relative orbital integrals, are equal up to some correction term that I have denoted here by a star, which is sometimes called a transfer factor. So these are all definitions, and now if you want to use those to compare the two relative trace formulae of Jacquet and Rallis, actually you would like to plug in the previous formulae two test functions, F and F prime, which you can write as product of local test functions, such that these local test functions are matching in the previous sense for all places V. And this requires at least two main local inputs, namely the first one, I mean, in order to have a comparison sufficiently general, is the existence of local transfer, saying that for every test function on one side, you can find a corresponding test function on the other side. So this is something which was proved in a very important work by Wei Zhong for non-Archimedean local fields, and subsequently extended to Archimedean fields by Heng Shui. So he has obtained a slightly weaker statement, which is however sufficient for all global applications. And then there's another local ingredient that is needed here, because when you write global test functions as product of local test functions, since the adels are a restricted product, these test functions have to be at almost all places the characteristic functions of the integral points. And therefore, we need at least to know that the characteristic functions of that integral points, they match at almost all places. This is usually called the fundamental lemma. And this part was actually proved soon after the paper of Jacquet and Rallis by Ziwei Yun in the positive characteristic setting using techniques, geometrical and cohomological techniques. And then it was it was transferred to a positive characteristic by Julia Gordon. And more recently, I gave another proof of that fundamental lemma working directly in characteristic zero, using as a main input some result from the work of Wei Zhong. So these are the two main local ingredients, but in order to complete the original approach of Jacquet and Rallis, it has to be completed by a fine analysis of the global relative trace formulas, and in particular, we have to deal with the analytical and convergence issues that I mentioned before. And this is a part of another series of talk. So first is the work of Michel Zidore and Chaudhary and Zidore, which have completely regularized actually the contribution of the singular orbits that I mentioned before. And this is giving you a completely general geometric size for your relative trace formulae. And then, so it remained to deal with the spectral sites. And in a recent paper with Yifeng Liu, Wei Zhang, and Xinwen Zhu, we were able to develop a new technique, which was quite general, to construct, in particular, spatial matching test functions as before, that have the good property of actually isolating parts of the automorphic spectrum, so that we can really concentrate on the part of the automorphic spectrum, which is important for the Gan-Gross-Prasad conjecture. And the last step was to study these contributions. And in work with Chaudhary and Zidore, we were able to regularize those parts and to find to describe a fine expansion of those parts to the relative trace formulae. And this, together with all the previous work, led to the proof of the Gan-Gross-Prasad conjecture and also to the Ichino-Ikeda conjecture. So I think I will skip the next slide where I was giving just an idea of the kind of results that we have obtained with Yifeng Liu, Wei Zhang, and Xinwen Zhu. So we'll move now directly to the local part of the story, which is kind of, so this is related to the global part, first because this was needed in the proof of the global results, but also it's a very natural complement to it. And it's in some sense a direct generalization of the results of Tunnel and Saito that I cited at the beginning. So here is the setting. It's essentially the same, except that we now take a quadratic extension of local fields, and we take them to be of character 0. And n is a positive integer. And as before, we consider a family of pairs of Hermitian spaces. And this time, I will rather fix the Hermitian line L to be given by the standard Hermitian form, H, which is just given by the norm of the extension, actually. And then for any n-dimensional Hermitian space W, you can do the same construction as before. So you construct the n+1 dimensional Hermitian space by adding to it the line L. And then you construct the two groups HW and GW. So G is just the product of the two unitary groups, and HW is a small unitary group that you embed diagonally in the product. So the question addressed by the local Gan-Gross-Prasad conjecture is actually the following one. So given irreducible representations of the two unitary groups, so pi W and pi V, you can form the tensor product. This is an irreducible representation of GW. And the aim is to describe the Ohm space from, the space of HW invariant linear forms on pi. And using this description of pi, you can see that it's actually the same as describing the space of UW intertwining operators from pi V to the contragradient of pi W. So that it's in some sense a branching law as described on my first slide. And one basic result in the theory is due to Heisenberg, Gurevich, Ravlich, and Schiffman in the periodic setting. And then in the Archimedean case, it was proved by Bin-Young Sun and Cheng-Bo Zhu. And it says that this Ohm space is actually always of dimension @-1, so that the only remaining question is when it is 0 and when it is not. And to answer this kind of question, we need a way to parameterize the reducible representations. In other words, we need an independent way to name the reducible representations of unitary groups. And this is exactly the subject of the local Langlands correspondence that I will very quickly review here for unitary groups. So what the local Langlands correspondence is doing, it is attaching to any reducible representation of a unitary group two invariants, or two names that are called L, which form a so-called L parameter, where the first ingredient phi here, so it can be actually described in very concrete terms for unitary groups. So the first ingredient here is a representation of the veil or veil-dealing group of the quadratic extension E, right? So it's a group which is closely related to the absolute group of E over a complex vector space M, satisfying certain natural conditions, so it has to be continuous and semi-simple, but most importantly, it satisfies certain condition of self-duality, or rather conjugate self-duality, which is also, so this is a kind of condition on the representation, which is analog to the self-duality condition, except that we take advantage of the fact that this is the very group of an extension of a given local field, so that we have also another outer automorphism. And this kind of condition, they come in actually in two flavors depending on a certain sign. And actually the sign here is prescribed by the dimension of the Hermitian space. So these are the first, these are the first ingredients entering into the local Lagrange correspondence. And the second ingredient, eta, actually, is obtained by first, so this can be described by first decomposing our representation phi into isotypic components, as any finite dimensional representations. This is semi-simple, so it can be decomposed into isotypic components. And then you collect among the irreducible constituents, among these isotypic components, the ones which corresponds to irreducible representations that are of the same type as phi, meaning that they should be conjugate self-dual of the same sign as phi. So you can collect all of them. This gives you a finite set I. And then the eta part of the parameter is just a bunch of signs indexed by this set of isotypic components. Okay. And so it turns out, so this is the local Lagrange correspondence is attaching to any irreducible representation such a pair. And it turns out that it sets a bijection actually between the set of all L parameters as described above and the union, disjoint union over all Hermitian spaces of a given dimension of the set of irreducible representations of the corresponding unitary groups. And in particular, it gives the compositions of each of these set of irreducible representations of one unitary groups into so-called packets. So these are L packets by V of phi. These are exactly the irreducible representations whose first part of the parameter is given is a given phi. And this is, okay, I should have mentioned this. This is also a consequence of the work I mentioned before of Mock and Kaleta, Mindiassin, and White, that this local Lagrange correspondence exists with good properties. And this is for the unitary group V. Of course, we can do the same for the small unitary group. So any irreducible representation there, we can attach a pair of parameters where phi prime is a conjugate self-dual of a certain sign, which is actually the opposite to the sign of phi. And eta prime is a bunch of signs indexed by the isotypic components having the same type as phi prime. And the correspondence actually, okay, it's not completely canonical. It depends on some choice. And this choice boils down to the choice of additive character psi e of E modulo F. So with this, I can now state the local result, so which is the local Gan-Gross-Prasad conjecture. So we start with the first, so phi and phi prime, these are L parameters, so but we forgot about the collection of signs for the moment. So these are just indexing L packets. These are parameters for UV and UW, so representations of the very Deligne group of E of dimension n+1 and n, which are conjugate self-dual for a certain sign. And then the main theorem is this one. So this was proved by myself in the PID case, and then and I proved a partial result in the Archimedean case, and then in the Archimedean case, it was proved by another method, first by Angu A, and then completed by work of Engshui, which is very recent. So the statement is as follows. So you assume that phi and phi prime are generic. So this is some technical condition saying that the packets corresponding to them contain generic representations. Then when you vary the Hermitian space as the small Hermitian space W, and take elements in the corresponding packets of UW and UV, there is a unique pair of such representations for which the previous Helm space is non-zero. And these representations are moreover parameterized by two sets of signs, eta and eta prime, and these sets are given by the following formulas, where, so these are given actually essentially by local root numbers obtained by tensoring. So phi I, remember, is the irreducible representations corresponding to the index I, appearing in the isotypic decomposition of phi, and the same for phi prime j. So these are these epsilon local root numbers of tensor products, and the local root numbers that depend on the additive character psi e, and actually to make it. So this additive character is related to the additive character we fixed to normalize the local Lagrange correspondence by a factor 2. Okay, and I should mention also that prior to this, a similar theorem was established in the PID case for special orthogonal groups by Waldspurger and Meuglin-Waldspurger. And more recently, it was also proved, again, for special orthogonal groups, but over Archimedean fields, that is over R, actually, by Zilin Luo and Cheng and Zilin Luo. So in the last slide, yes, I will just give a very short glimpse at the proof of that last theorem. So the basic idea is to assume that H and G are compact. So in this case, there is a very simple formula for the dimension of the Helm space we're interested in. Namely, by standard character theory, this is given by integrating the usual character. So in this case, pi is finite dimensional. It has a well-defined character given by taking the trace of that representation. And the dimension of that Helm space is just the integral of that character of H. So that's a consequence of the orthonormality relations of characters, which you can rewrite, because the character is an invariant function, as an integral for some suitable measure over the space of conjugacy classes in H of the character. And something which is very stunning and that was discovered by Waldspurger is that actually a similar formula exists or sometimes exists even when H and G are non-compact. So namely in the setting that we actually have a formula of the following form. So for the dimension still of the Helm space, we have a formula where we integrate on the right, we integrate a certain character which is called the Archandra character of pi. So in this case, it's not defined directly by taking a trace of the representation because the representation is infinite dimensional and it doesn't make sense. So there is a way to define such a character using a distribution theory, that's what's done by Archandra, and then we have to regularize it because it's not well defined everywhere, and integrating it over some set of conjugacy classes. So this is a formula that can be actually proved essentially by using again some kind of relative trace formula. And this relative trace formula, very roughly speaking, is actually computing in some sense the trace for the action by convolution of a test function on G on the L2 space of G mod H. Okay, so I will not say more about this. But then the second question is, once you have this, how you prove the Gan-Gross-Prasad conjecture, since it is telling you that this dimension is related to epsilon factors. So the point is that actually there is also a similar formula for epsilon factors, which is obtained essentially by replacing the pair HG by another pair H prime G prime, which is the one we have already encountered before. So take G prime to be GLN times GLN plus 1 over E, and H prime is this GLN sitting diagonally in the product. And then we have some action again of test function on G prime on the L2 space of the quotient. But actually we can define a twisted trace, that is a trace for the operator composed with a certain automorphism of the situation, and computing this twisted trace essentially in the same way as before, this leads to a similar formula for epsilon factors of pairs. And at the very end, we can link the two by the theory of endoscopy, which is very roughly speaking expressing the Archandra characters of irreducible representations on unitary groups in terms of the characters that so-called twisted characters that are appearing in the formula for epsilon factors. Okay, so I think I should stop just right there. So thank you very much for your attention.